Hello everybody, welcome back to our explanatory videos. This is the last one corresponding to chapter 7.4, I should say paragraph 7.4. And in this video we're going to use our formula to analyze collisions. The previous time we used the formula for braking. We realized that when you want to know the time to come to a stop, you must also account for reaction time. And during your reaction time, your vehicle will remain at a constant speed. For the time during braking, you can use the force formula. If you want to know the braking path, you can, but you have to realize that when you are braking, your velocity is not a constant. It drops. So to calculate the braking path, you have to use average velocity. Now, a collision is basically braking, but in a very, very short time. So we're going to look at eggs being dropped on the ground. And basically the force that is causing them to stop is the force exerted by the ground on the egg. And since the ground cannot be suppressed, this will be a very short time. Okay, I already watched it here, but so it kind of gave away the surprise. Okay, so this was filmed at a very high frame rate. So 1 second in reality is thousands of frames. And you can see very quickly the egg is brought to a standstill. This will take, well, maybe a millisecond or so. Now there are ways to let an egg drop without it breaking. And that is shown here. This was a contest between students who were challenged to build something to let an egg drop from quite a big height without it cracking when it hits the ground. And as you can see, of things, some used boxes, some used cylinders. I believe now there comes a beautiful one where egg is suspended in pieces of rubber band, and all these eggs survived a drop from at least 3 meters, which would usually never happen. So I want to use our formula to find out why these eggs are not cracking when they hit the ground. The idea is always the same. All contestants tried to make the time required to come to a stop longer. If you take a look at our formula, you can see why that works. For braking was m times v start. So let us suppose that we have eggs dropping, they all have the same mass and they all hit the ground with the same speed. You have to realize here that v start is the speed with which the egg hits the ground. So imagine the egg being touching the ground, but it hasn't cracked yet. Now, if the time required for the egg to lose all its speed is very short, that automatically means the force on the egg becomes very large, similar the way we have seen with the safety belts in the egg. So what causes the egg to crack is basically the enormous force. If we can find a way to let the crash, then the force on the egg will be much smaller. And this could, for example, be done by wrapping the egg in cotton wool or aluminium foil or anything that can crumble. So if this egg hits the ground, before it comes to a standstill, first this paper or whatever it is, cotton wool, has to be pressed together. and only then the egg will hit the ground. So the total collision lasts longer, and therefore the force becomes smaller. Let's use our formula in a calculation to see how this works. So, I want to calculate the force on an egg. So, we're going to assume that when we drop an egg to the ground, that the time it needs to break is about a millisecond, which is 1,000th of a second. When we wrap it in cotton wool for protection, then it will take a little longer because the cotton wool has to be compressed first. Let's suppose it takes 10 milliseconds, 10 times as long. That is still a very short time. It's 100th part of a second. But it makes quite a big difference. Let's suppose the mass of the egg is 100 grams, that's 0.1 kilograms, and that it hits the ground with 10 meters per second. All easy numbers, easy to calculate. So, first the unprotected egg. F times t, we want to calculate the force on the egg. The time was 0.001 seconds. The mass was 0.1 and the speed was 10, which together equals 1. So the force on the egg would be 1 divided by 0.001, which equals 1,000 newtons. Now the protected egg, prot egg. We use the same formula. We're solving for F. However, this time the time required to bring the egg to a standstill is only 0.01 seconds. Mass and velocity are the same. So the force on the egg would equal 1 divided by 0.01, which equals 100 newtons. So the force has been reduced by a factor of 10, and that is actually quite a lot. To give you a bit of an image, 10 kilograms of mass equals 100 newtons. So if you want to lift 10 kilograms, you need 100 newtons. This would still be more than enough force to crack the egg. So we probably need to make the time a bit shorter. But 1,000 newtons is what you would need to lift 100 kilograms. So this is actually quite a big reduction. Lengthening the time that the crash takes really works. Now, let's apply this theory to car crashes. A car crash always consists of two crashes. The front of the car hits something, and during that time the front part of your car is crumpled. This is called the crumple zone. And basically this is also meant to keep the passengers safe. Because crumpling the crumple zone, the front bit of your car, takes time. And therefore it makes the total crash time longer, and the force on the person in the car makes it less. Then there's the second collision. That's when the head actually hits the wheel. But before that happens, you have your safety belt, which stretches. Again, because the safety belt needs to stretch, the time to come to a full standstill becomes longer, and therefore the force on the person inside the car becomes longer. Airbag, same idea. Because your head hits a cushion of air instead of the steering wheel, you have more time before your head comes to a standstill. If you wouldn't have these safety measures, then for your head to stop would fully be accomplished by you hitting the wheel, so it would take milliseconds or less, which makes the force on your head incredibly high. All these safety measures have the same idea: make the crash last longer. So, we're going to look at an example to see how this works. We have a car without airbags, I'm afraid, but it does have a crumbling zone, which is marked with X, and it has a safety belt marked as Y. The car crashes at 20 meters per second, and the first thing that happens is that the front is pushed inward. So the first braking starts here, 0.6 meters. That's the first collision. Then when that has happened, the safety belt stretches by 0.3 meters. That's the second collision. I want to know how high is the force on the driver if he weighs 75 kilograms. So, to know this, we have to look at our force formula. Force times time equals mass times v start. Number of things we can fill in. We know the driver has a mass of 75 kilograms. We also know its starting speed, that's 20. The F we want to know, so I don't fill that in. Then we need the time it takes for this person to come to a stop. I don't know that one yet, so that's what we have to find out. Let's see how far he moves. The total distance covered by this man in the car from the moment the car hits an obstacle is basically the distance of the crumbling zone. He moves 0.6 meters. And the distance of the stretching of the seat belt, which is 0.3 meters. So he has to stop while traveling 0.9 meters. As we have said, when you are braking, decelerating, your speed is dropping. So we can use S equals V average times T to find out how long it took for him to stop, but we need to know the average velocity. I'm going to rework this formula so that we have T equals V, we have S equals, T equals S divided by V average. And then we need to know V average first. We know that the final speed is the starting speed is 20 meters per second, and the final speed is 0. If you divide that by 2, we find an average velocity of 10 meters per second. I'm going to fill that in. Distance was 0.9. Average velocity 10 meters per second. So the time required to stop is 0.09 seconds. This I'm going to plug into my force formula. I can now see that the force would equal 75 times 20 divided by 0.09. Let's type that in. Okay, this results in, rounded off, 1.7 times 10 to the power of 4 newtons. Now this is still quite big. So you will probably hurt yourself still quite a lot. But just remember that if this crumple zone wasn't here, and if this safety belt wasn't here, then the time required to stop would be much smaller even. So the force would be much higher then. Conclusions. To reduce the force of a crash, you have to make the crash last longer. In car crashes, this is done with a crumpling zone, airbags and a safety belt. To analyze these kind of crashes with the known formula, you need to realize that the time is the time required for the crashing object to come to a standstill, and the force would be the force of the crash. This concludes our explanation video. Have a good week and see you all in class.